Hello and welcome to the 6.3 notes. This is a brand new section over volumes. And what we're going to do is we're going to find volumes of irregular shapes. So let's come in here and let's write that when we're talking about volumes in calculus, these are of irregular shapes. Okay, so we have some techniques to calculate the volumes of irregular shapes. And the first one that we have is volume by cross sections. And what I'd like to think of is a loaf of bread. Okay, so if we think of this loaf of bread that's kind of an irregular shape, and we want to calculate the volume of this loaf of bread. And one technique we could do is the cross-section method, which is essentially the idea is that we would cut this bread into slices. We would calculate the volume of each slice and add them together, okay? So when we talk about volumes of cross-sections, I like to think of, what's right here, find the volume of a loaf of bread by adding the volumes of the slices. Okay, so let's take a look at these pictures over here. This is kind of a standard example of just a picture of what we're doing. And the method that we would use to calculate the volume of these irregular shapes is by taking the shape and slicing it up into a bunch of different pieces. And what we notice is that when we slice this, we get this same cross-sectional area at any point along, at any x value, okay? And so what we can then do is we can then take the thickness, take the cross-sectional area, and then give it a little bit of thickness, and then add up all those slices, okay, much like the sliced bread. So the first thing I want to do is kind of go over the formula that we have here. And so, our general slicing method using the cross sections is that to find the volume of this shape, we would want to integrate from, the x values from a to b of this function a of x. Now, a of x, it's important that we note that this is the area of the cross section. Okay, which we'll also kind of call the slice, okay? The area of the cross-section, okay? Now this dx, okay, this is the thickness, okay? So when we think about, multiplying the area of a cross-sectional base and then multiplying it by a thickness, this gives us volume, okay? So if you remember back to geometry, that's what we did. So let's take a look at this first example. And what we're trying to do is create a solid on a fixed base. And the fixed base that we have is a circle of radius 1. Okay, so we want to find the volume if the cross sections to a fixed diameter of a circular base are squares. So we have this fixed base, and what we're going to do is we're going to create these squares that will move across the entire circle and create the solid, okay? So let's go ahead and let me show you guys an animation real quick on how this all works. And so I'm going to go ahead and kind of play this and explain it as it goes. So what we have is we first have this circle, and if we drop this circle down flat and look at it on a base, we can put squares inside of this circle at any point along, any point along the diameter. So what happens is as we create these squares, the size of the squares changes depending on the x value. And as we drag this across, we get this, this solid figure that's created by taking all these different squares and dragging them across the base of a circle, okay? And so as we move these squares across, the squares start to get bigger and bigger and bigger. And then, and so they get bigger and bigger and bigger and bigger, and then they get smaller. So there's an infinite number of squares inside of this circle, and we want to add up all those little squares, okay? And we want to calculate the volume. So let's go ahead and talk about how we would do that. Let me go ahead and stop this real quick. And let me come back over here. And the first thing I want to do is to write an equation for this circular base, okay, of radius 1. And so we have this general form of a circle, which is y equals plus or minus the square root of the radius squared minus the x value squared. So because our radius is 1, we have the equation y equals plus or minus the square root of 1 minus x squared. So let me come down here, and I'm going to kind of highlight this circle for you. And so this top part, the part that's positive, this is y equals the positive square root of 1 minus x squared. Okay, and this bottom part is y equals negative square root of 1 minus x squared. Now, what I want to do is I want to come up with a general formula for the area of one of these slices, okay? Now, what you have to remember is that this slice changes depending on where you're at along the circle, okay? So what I can do is I actually want to figure out a way for me to create a formula for any cross section at any point in between -1 and 1. So what I want to do is I want to come up with this function a of x. Okay, so a of x, and this is the area of my cross section. So when I think about the area of a square, so when I think of like the area of a square, we got to think of that formula, and that area is equal to the side length squared, okay? And so the question is how do I get this length here? Okay, how do I go from one function to the next? Okay, and we did that in the last section, where we found the distance between two functions, okay, or the area between two functions. So we have to think of top minus bottom. So if I think of this side length s, okay, and I'm going to call this side length s here, that side length s is equal to the top function, which is the square root of 1 minus x squared, minus the bottom function, so minus negative square root of 1 minus x squared. Okay, and if I subtract a negative, that really means I'm just adding them together. So if I have two of these radicals, then I just have 2 times the square root of 1 minus x squared. So that is my side length here. Okay, now because this is a square, that side length is over here as well. So we kind of have to put all this stuff together and say, okay, if I wanted to find my area in terms of x at any point, I would take the side length and square it. Okay, so my side length is 2 times the square root of 1 minus x squared. So my area function is just going to be the quantity 2 times the square root of 1 minus x squared quantity squared. Okay, and so if we wanted to calculate the volume of this, then what we would do to calculate the volume, we would just integrate from -1 to 1 of my area function, a of x dx. Okay, so this is equal to the integral from -1 to 1 of, and I'm going to do 2 times the square root of 1 minus x squared, this whole quantity squared dx. And this is an integral that will give us our volume, okay? And you could even simplify this a little bit. Obviously you can leave it in this form, but if you're being asked to simplify and evaluate, then you'd want to integrate from -1 to 1 of 4 times the quantity, 1 minus x squared dx, okay? And we could do this by hand, but I just want to set these up. So that is how we would set up an integral to find the volume, okay? Let's take a look at another one real quick. And we want to do a very similar problem, but we want to find the volume of a figure on a fixed circular base. So here's our circle again. If our slices are equilateral triangles, okay? So let me show you guys the animation of what this is going to look like real quick. And so it's going to be a very similar task that we just did. So we want to drop this circle flat. Okay, we want to use equilateral triangles that are determined by the base of that is our circle. Okay, so as we drag this triangle across this circle, what we notice is that the triangles get bigger and bigger and bigger and bigger to about the center, and then they start to get smaller again. So again, the triangles are determined by the base of the circle, okay? And so we get this kind of irregular shape that we're going to find the volume of, okay? So what we need to do is we need to calculate the area, or find the area of one of these triangles, okay? And so the thing that we need to remember here is that the area of an equilateral triangle is equal to the square root of 3 divided by 4 times the base squared, okay? And so this is something that I've derived using geometry and using a 30, 60, 90 triangle. You guys can come up with this on your own. We'll talk about that more in class as far as how to get that. But what I want to do is I want to, draw my circle here real quick, okay? And this is a circle of radius 1, so the equation is y is equal to plus or minus the square root of 1 minus x squared. Okay, so this is y equals the square root of 1 minus x squared. This half circle down here is y equals negative square root of 1 minus x squared. Okay, and then let's look at one of these slices real quick. Okay, and so here's my base of that slice, okay? And so remember that our base from the previous example, because we're doing this on the same one, the length of that base is just going to be 2 times the square root of 1 minus x squared, okay? And so if I wanted to come up with a formula for the area of my cross-section, then it's just going to be, the square root of 3 over 4 times the base squared. So I want to take this base and substitute it in. And so we get this formula for the area, a of x is equal to the square root of 3 over 4 times the quantity, 2 times the square root of 1 minus x squared squared. Okay? So now if we wanted to find the volume, okay, remember the volume is equal to the integral from -1 to 1 of our area of the cross-section, dx. And so let's plug in our area function for this equilateral triangle. So from -1 to 1 of the square root of 3 over 4 times the quantity 2 times the square root of 1 minus x squared, that quantity squared dx. Okay, and this could be simplified, and we could say the integral from -1 to 1 of the square root of 3 over 4 times the quantity 4 times the quantity 1 minus x squared dx. And then these 4's would actually divide out. So we could then actually write this as the integral from -1 to 1 of the square root of 3 times 1 minus x squared dx, and we could integrate from there. Again, we are just concerned about setting these up right now, but you still need to know how to do them by hand. So let's take a look at another example real quick, where we have the same circular base, and we have isosceles right triangles as our cross-sectional area. So let me show you guys a quick little video on that, and then we'll set this up. So if we drop our y-axis flat, and if we look at these triangles, they are isosceles right triangles. And so what we notice is that, again, the triangles will get bigger and bigger and bigger as we move across the x-axis and get smaller as we get to the other side, because the base of the triangle here is determined by the distances between our curves of our base, okay? And so it's an isosceles right triangle, so my base is the same as the height, and so it really shouldn't be too terrible of a problem to set up, but I'm just wanting to show you guys that this is what the figure looks like, and we get that by dragging an isosceles right triangle across that entire base, okay? So let's take a look at this last example real quick and set this one up. Let me get my circular base ready. This is y equals the positive square root of 1 minus x squared. This one down here is y equals the negative square root of 1 minus x squared. Let me draw in my triangle slice. Here's my base. This is also my base, okay, because these two segments are congruent. So my base length, again, is equal to just 2 times the square root of 1 minus x squared, all right? And so we want to integrate our volume from -1 to 1 of our area function, a of x dx. So remember our area, okay, and hold on, over here. Area of a triangle is the base times the height divided by 2. Okay, our base and our height are the same thing. They're both bases, so our area is going to be b squared over 2, or you could write that as 1/2 times b squared, doesn't matter. So if we wanted a formula for our area, a of x, okay, that would just be this base squared and then divide it by 2. So we've got 2 times the square root of 1 minus x squared, this quantity squared over 2. Okay, so let's go ahead and plug that in real quick into our volume, into our integral function. And so we've got -1 to 1 of the quantity 2 times the square root of 1 minus x squared, this quantity squared, all over 2 dx. And we could simplify this, and we could get the integral from -1 to 1 of 4 times 1 minus x squared over 2 dx. And then the 4 and the 2 divide out, so we just get the integral from -1 to 1 of 2 times 1 minus x squared dx. So I'm going to do one more example with this, but I'm doing it on another video. I hope that this is reasonable. It may take you a few, you may want to watch this video a couple times to exactly see what I'm doing. But I hope you enjoyed it, and we'll see you soon. Thanks. Bye.